All right, in the last phase of our chapter, we are going to study uniform series analysis. This part is especially important, my friends, because if you understand how to analyze uniform series, then it is just going to make your life easier in the future part of this course, because in the rest of the course, we are basically dealing with the conversion between the uniform series and other type of series to present value and the future value. So it is best at this point you study this chapter very well, and this is just going to help you a lot in the future chapters. Okay, so what is a uniform series? A uniform series is basically an equal amount of annual cash flows. Okay, remember now we have told previously, until a certain part of this course, until a certain chapter, we are just going to assume that every transaction is made in the end of the years. Okay, so the period of our problems for a while are just going to be years. However, in real life economical problems, you know, the transactions are made on a weekly basis or a monthly basis or daily basis. So we have different time cuts to study a cash flow diagram. However, just for simplification purposes, we are just going to assume that at this moment, the transactions are made on a yearly basis, okay, annual basis. So you see, a uniform series analysis deals with equal amount of annual cash flows. And what is an annuity? Annuity is a series of payments made at equal time intervals. And at this point, we are just assuming these time intervals are just years. Okay, so you see, we have a horizontal line that represents the flow of the time. And for n years here, in the end of every year, there is a negative cash flow of size A, okay? And that A is basically representing the annuity size, okay? The payments here in this uniform series are usually denoted with letter A, and the question that we would like to ask is basically this. If we amount at the end of each year for n years into a savings account, and if that savings account is compounding or investment with an interest rate I per year, in that case, what would be the total accumulated amount in the end of the n years? Okay, so the question is basically asking this. How are we going to determine the future value of the uniform series? This time we are not converting a present value, an initial principal. This time we are making investments at equal time intervals, which are basically years at this moment, and we are asking the future value of these annual payments. Now, how are we going to solve this problem? We are just going to handle each transaction one by one first. So we are just going to ask, what is the future value of our first transaction in the end of n years? What is the future value of the second year's transaction in the end of n years, so on and so forth. So each annual amount, each installment, so what we call these annuities are also installments, okay? So installment in Turkish means taksit. So each installment is going to bring us a certain future value, and the future value of the uniform series is the total of the future values created by each installment. Now, the first installment A is going to compound for n-1 years, as you can see from the end of the first year until the end of the nth year. There are n-1 years, and using the single payment compound amount factor formulation, we will say that first installment A is going to be compounded to a future value of f1 by multiplying with 1 plus I to the power n-1, where I is the annual compounding interest rate, and n-1 is the number of years that money is going to be kept in the account. Similarly, the future value of the second installment would be f2, that is A times 1 plus I to the power n-2. because it is going to be kept in the account for n minus 2 years. Any installment that is made in the end of year K, which is called our K deposit, it is going to be kept in the account for n minus K more years until it matures, and the future value of the Kth installment would be a times 1 plus I to the power n minus K. Finally, the last installment is not going to be compounded because the future value is measured at the end of the nth year, and we are making this payment just before that, and it is not going to be compounded at all. Therefore, the future value of the last installment is going to be simply A, okay, because there is not any time period that this last installment is kept in the account, therefore it cannot gain any interest. Okay, now how can we calculate the future value? The future value can be calculated by summing the future worth of each installment up. So the future value of the uniform series is calculated by summing the future worth of each installment. And we have already formulated these future values in terms of the installment size A and the compound amount factors. Now, here you see, because we have equal sized payments in the end of each year, A here becomes a common multiplier, which can take out of the summation, and the rest of the sum is a sum of the compound amount factors of 1 plus I to the power K as K changes from 0 to n minus 1. Okay. Now, this summation or this series is called the geometric progression. There is a simplified formula for the summation. This summation becomes equal to 1 plus I to the power n minus 1 over I. Okay. So at this point, let us show. So we are going to come back to this page and we are going to study the rest. But at this point, let us show how come this summation becomes exactly equal to the formula of 1 plus I to the power n minus 1 over I. So we are just going to skip to page 20, and we will show that the geometric progression here, summation of 1 plus I to the power k values, as k changes from 0 to n minus 1, equals to 1 plus I to the power n minus 1 over I. We are just going to assume that I is greater than 0 because the interest rate cannot be negative. And we are going to expand this summation by plugging in k values from 0 to n minus 1. When k is equal to 0, the first term becomes 1. When k is equal to 1, the second term becomes 1 plus I. When k is equal to 2, the component becomes 1 plus I to the power 2, so and so forth, okay, until the last component, 1 plus I to the power n minus 1. Now, the magic trick here is to multiply this summation with 1 minus 1 plus I and divide it with the same value again. And if we do that, the result will not change, because 1 minus 1 plus I is basically equal to minus I. So we are basically multiplying this summation with minus I and dividing it to minus I. The result wouldn't be affected. Now, we are writing minus I in the form of 1 minus 1 plus I for a spatial purpose, because if we do that, first we are going to multiply this summation with 1, then we are going to multiply this summation with minus 1 plus I. And when you multiply this summation, this series, with 1, you are exactly going to get the same series. And when you multiply this series with minus 1 plus I, you will get a minus sign first. Then every term here is going to be multiplied with 1 plus I, and your series will become a summation starting from 1 plus I, increasing the power up to n. Okay. Now, after doing that, you will easily realize that from the terms in the first summation from 1 plus I to the power n minus 1, they exist in the second summation as well. So they will simply cancel out by the minus sign, negative sign between these two series. In fact, in the numerator, only two components will be left. The 1 coming from the first series and 1 plus I to the power n coming from the second series, which is going to be subtracted. And in the denominator, remember, as we have multiplied the numerator with 1 minus 1 plus I, we are dividing it as well. And in the denominator, we are simply going to get a minus I. And after multiplying the numerator and the denominator with a negative 1, you are going to get 1 plus I to the power n minus 1 divided by I. So this is how this geometric progression is simplified as 1 plus I to the power n minus 1 over I. Now, if we go back to 2 slides before, you see that if we have equal sized annual payments made in the end of each year for n years, under an interest rate of I% per year compounding annually, the future value that is accumulated by these annual payments would be calculated as the size of a single installment times 1 plus I to the power n minus 1 over I. So this formula here, the ratio between the future value and the installment size in an annuity, is called the uniform series compound amount factor, and it helps us to calculate the total accumulated future value by a uniform series by multiplying the size of an installment with that factor. Now, as we have previously mentioned, we will be using the extended notation in this class to understand or solve many types of problems, and the uniform series compound amount factor will be represented by this notation, parenthesis f over a, under I% interest rate for n years. And that formula, the extended notation, represents the formula of 1 plus I to the power n minus 1 over I. Okay. Now, remember, we had a table which is called the annual compound interest table. And we can either, in a problem, we can either use this formulation to solve the problem, or we can just try to find or identify the compound amount factor using an extended notation from the compound interest table. Now, in this question, we are going to do the both. We are going to see how the solutions will change if we use the formula directly or we use the table. The question says, a student plans to deposit $600 each year in a savings account over a period of 10 years. So you see in this page 17, assume that you have 10 years only, so n is equal to 10, and the student is depositing equal amounts of money at $600 for 10 years. Now, in that savings account, the bank pays interest at a rate of 6% per year, compounded annually. In that case, how much money will have accumulated at the end of 10-year period? So if you draw the cash flow diagram of this question, you are just going to draw a horizontal line for n equal to 10 years. And in the end of each year, there will be a $600 of deposit from the student's perspective. And the question is basically asking the future value in the end of these 10 years. And we know for annual installment sizes are $600, the annual compounding interest rate is 0.06, and the number of years, investment years, is equal to 10. Either you can use the formula, you can say the future value of this uniform series of cash flows is equal to the annual installment size times the uniform series compound amount factor. Then what you do is plugging in the values. A is equal to $600. The annual compounding interest rate is 0.06, and the number of investment years is equal to 10. And the result would be $7,908.48. Now, the total investment amount is basically $6,000 by the student. However, through the years, every installment is going to be compounded with interest rate of 6%. In the end of 10 years, the student is going to have more money than he has invested. Now, how can we use the other way? How can we use the compound interest table and the extended notation? Now, the extended notation is much more practical in many cases, my friends, okay? Formulas are always giving you the exact value, so the good side of formulas is this, but the bad side is sometimes they are too complicated to implement in a calculator or sometimes in a computer environment. Now, through the compound interest table, we will say that f, the future value, is equal to the annual installment size times the uniform series compound amount factor, which converts the uniform series to the future value. And that formula is, that notation is f over a under I% interest rate for n years. Okay. So in this practice, in this question, we are multiplying an installment size of 600 with a uniform series compound amount factor f over a under 6% interest rate for 10 years. And if you multiply a with f over a, a's will cancel out, and what you are going to get is the future value. Now, we need to check the uniform series compound amount factor f over a under 6% interest rate for 10 years from our table. And now we are just going to switch to our table. Now you see in this table we have every page corresponding to a certain interest rate, and in each page we have the uniform series compound amount factors in the second column for different number of investment years on the rows. So what I'm going to do is I'm just going to move forward a few pages until I reach to 6% interest rate here. And the uniform series compound amount factor f over a for 10 investment years is 13.1808. So I'm just directly going to use this value in my calculation. I'm just going to replace this extended notation with the value that I have found from the table, and that is going to make $7,908.48 for the solution of this problem. Now, we have already shown the geometric progression proof, and we are going to study the uniform series sinking fund factor in the next video.